Wow, there we go. All right, so we are recording. I think the mic is good. And so today we're going to start with this new topic, which is propositional logic. And it's a pretty drawn out module, even with compared to all my other module, this one is kind of drawn out. But at the same time, I think it does have a lot of relevance to the AI topic that we talked about in the previous class. With automated reasoning. It's just generally speaking interesting. Um, so we're going to get started here. All right. So before I start, do we have any questions about anything that I should answer? Yep. Um, so a scanned copy should be in a share folder that you have access to. If you prefer to risk paper cut, I can give you the paper copy. I'm trying to save your skin when I don't give you the paper copy, but if you insist on getting a paper copy, that's fine too. I can, in fact, I think they're all, oh, I brought it in my office. So you can follow me to the office if you want to get your paper back. Yep. All right. Any other questions? No other questions? So next week is spring break. Okay. Just want to remind people, just in case somebody does not know and come back here on Monday. It's like, where's everybody? Nope, we're all in spring break. Okay. All right. So we're going to get started with propositional logic, and I will just kind of go step by step and kind of go slow with this one, okay? So propositional logic is about proofs. In other words, you are going to prove something is either you're going to prove a particular statement is true based on a bunch of things that are assumed. Okay, so I will tell you this is true, this is true, this is false. Okay, those are the starting premises, and then using logic, you can then prove a particular statement is true also. Okay, so I know it sounds really abstract. So hopefully, as we go along, it will be a little bit more clear as to what they mean by, oh, okay, something is being true, this is a given, and how do we derive the truthfulness of another statement? Okay, I can give you an example to start with. Okay, so we'll go ahead and start with an example. And let me see. I think using the tablet is probably better today because um, you being able to see the arrows, to look at the connection between the statements, can be helpful, from the visual perspective. So we're going to do that. And let me get this connected. Okay, very good. And then starting on this side, Supernote. Oh, okay, it connects right away. Sometimes it connects right away, and sometimes I need to nudge it a little bit to make the connection. Okay. So we'll go ahead and start with some variables, okay? So let's say, variable p, which is a Boolean variable, and p as a variable is either true or false because it's a Boolean. And let's just say that, okay, I have to be careful because propositional logic cannot handle quantifiers. So I cannot use, every, none, some, at least one. It cannot handle that. That's the job of predicate logic, which is a different logic system. It is related to propositional logic, but it is not the same. Okay, so I can do something like, oh, okay, I know what to do. So we can say, a blue cat is sick. Um, okay, and then Q, and you probably know what it is already. Uh, Today is doomsday. Yep, today is doomsday. All right, and then we have, so these two are variables. In other words, I'm just assigning values or meanings to P and Q, okay? So now I'm going to give you, so these two are just, definitions, DEFN. They're just definitions. What does P mean? Okay, P is just a variable. Instead of saying a blue cat is sick all the time, I'm just going to say P. Okay, whether P is true or not depends on whether a blue cat is sick or not. Okay, same thing for Q. So these are just definitions. So now, we will start with statements. Statements known to be true. Okay. And we are going to start with P implies Q. So P implies Q is a statement that is known to be true. So don't question it because it is an axiom. Okay, it's axiomatic that in this case P implies Q. Okay, and also on top of this, I would also say not Q is also true. Now, you can say, but tech, or you can also say Q is false. Okay. Well, that is true. Okay. But in propositional logic, we focus on the statements that are true. So if you have a statement that's known to be false, you have to say, oh, the negation of that is true. Is that okay? So we focus on statements that are known to be true. So this is known. Okay. Statements known to be true. So now I want to prove, okay, one way or another, P is also false. In other words, I want to use these things. So these are statements known to be true. They're given to you. And now I'm interested in a proposed theorem. Okay, this is my proposed theorem, which is not P. So now the question is, can it be derived? In other words, can somehow I link up, P implies Q, not Q, and somehow use a mesh of implications so that eventually I can show that not P is true. That is what propositional logic can do. Is that okay? All right. But as I said a little bit earlier, it does have a lot of limitations. It cannot handle quantifiers. So it does not understand, nor can it handle something like, oh, every, at least one, none of, blah, blah, blah. So it cannot handle those. Are we doing okay so far? Kind of in terms of, what propositional logic can help with. Okay, all right. And just so that the importance of propositional logic or something like this in terms of quote unquote automated reasoning, I will show you an exam question from CISP 310, the first exam question for CISP 310, because that one actually has a lot of logical stuff, which is what propositional logic is really good at. So let me show you that particular question. It is in. All right, so this is already 310, and this is the right file. Magical. Okay. All right. So for what we need to understand in this class, the context is not important. The context of this particular question has to do with binary subtraction. Okay, how do you subtract numbers when you have only zeros and ones? So the basic rules of zeros and ones do not really, the basic rules of multi-digit subtraction does not change. Okay, you can still say, oh, if you subtract one from zero, because one is greater than zero, you would end up with a carry. Okay, so those concepts do not change. But what does change is in binary subtraction, we can replace arithmetic operations like greater than, less than, adding one, okay? We can replace all of those with logic gates. In other words, everything translates to negation, conjunction, and disjunction so that you can actually implement the operation using transistors, okay? But that's outside of the context of CISP 440. So what we want to know is how things are defined, okay? So for whatever reason that is not important in this class, T2 is defined as the negation this is the logical negation or not. This is not x1 and y1 or not q1 and t1. So in this class, we talk about these alternative notations already as well. Okay, so this is using the alternative notation for Boolean expressions. Okay, so basically a bunch of stuff is defined, and I need to know why. And L of zero is also, L equals to zero is also by definition or axiomatic in this case. It is given. Don't ask me why. So now I want to know why D1 exclusive OR with O is also a zero. So in this case, it is because how um, D1 exclusive OR with O is actually how they are defined. So there's an equality here. And we also know that L itself is a zero. So between 7 and 9, we can deduce 12. So the entire exercise is about this. Okay. Um, when this question was fed to ChatGPT, it was able to figure out most of the answers. It was able to go like, okay, based on what we already know, I can now figure out why the negation of Q0 and T0 is zero based on everything before 25. There are a few that it cannot figure out. So there are a few, it goes like, okay, we'll just assume this is by definition. It just doesn't understand how to apply that logic, which is ironic because if you think about it, your ChatGPT is based on computers, and computers are based on transistors, which means they're all based on logic gates, and yet it cannot solve a logical problem like this. Okay, the importance of that is there are definitely things that computers cannot do or AIs cannot do just yet. Okay, so we want to look into a mechanism that might help AI to be able to finish to complete those particular tasks because that's kind of the focus. Remember last time I showed you guys the article that talks about how Amazon is using ancient Greek logic to remedy some of the issues of how AI operates, in today's iteration. All right. So now we're going to go ahead and say, okay, but what else do we need? Okay, now I'm switching back to Supernote here. So the question now is, what else do we need in order to show one way or another? Okay, because I can show you something that is not a theorem. So you still have to make a conclusion of saying, oh, that is not a theorem. Okay, it cannot be logically deduced. So in other words, I can say, what if I change the proposed theorem to just P? Okay, well, in that case, it is not a theorem. So the algorithm cannot just go like, oh, I'm going to spend more time to try to think about this. I cannot answer the question right now indefinitely. Okay, so we need to find out, okay, which one of these is a theorem based on P implies Q is known to be true, not Q is also known to be true. All right, so that's kind of the backdrop, of what we want to be able to accomplish. So now we're going to talk about the mechanism, the actual very mechanical aspect of how propositional logic works. So do we have any questions about, what this is about, what propositional logic is supposed to be to accomplish in the context of what we're trying to solve here. So is that part okay? Yep. You're kind of soft. I need to hear. So the question is, what is a theorem? So let's just say that. Um, okay, so we'll focus on something else. Okay, there we go. So let's just say that, A is representing a statement, B is representing a statement, C is also representing a statement. A statement that is true. Okay, so A, B, and C in this example, they're all statements that are known to be true. In other words, don't ask me why they're true, they're just axiomatically true. Is that okay? And I have another statement called D over here that I need to know whether its truthfulness can be implied by A, B, C. If I know A is true, B is true, and C is true, can I deduce that D is true as a result? That's the question. If it can, in other words, if I go through a bunch of implications, okay, if I go through a bunch of implications, it can be a mash of implications, okay? It can be a mash of implications where this goes into here, and then this eventually goes here, blah, 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 okay? But eventually, let's just say that D is implied. That means D is a theorem with respect to A, B, C. Is that okay? Now, I think this particular aspect of what a theorem really is usually not explicitly stated, even in your math class. But in this class, because our focus is logic, so I have to basically tell you guys, okay, what does it mean when I said, D is a proposed theorem? The question is, can I make a mash of these implications and eventually end up with being able to say that ABC implies D? That really is the question. Yes. We are not concerned about whether D is true or not. We are concerned about whether if A, B, and C are all true, can that imply D? That is the question. To be more exact, each of those steps is an implication. So we are looking at a mesh of implications that start off with ABC, but eventually the implications all lead to D. So eventually we can say through a chain of implications, ABC implies D. Now, is D actually true? We don't know because A, B, or C may not be true by themselves. So we are not really concerned about whether A, B, and C are all true. We are not really concerned about D. We are concerned about the implication between A, B, C, the given statements that are true, and the statement that we think is a theorem, which is D. Yep. Um, That would be that is not a logical deduction because you're looking at natural phenomenon and based on observation, that's usually what happens. But we are looking at things that are definitely just logical, so it's entirely black and white based on logic. Something like that. Yes. So it has and or not, involved. And everything is really rigid or rigorous, in this case. In other words, it's not based on probability. It's not like, oh, 90% of the time, if this is true and this is true, that usually is true. We are not concerned about probability at all with this topic. This is all logical, which means everything is black and white. Yep, go ahead. As long as whatever you're concerned about is implied by A, B, and C. If it can be implied. That's the focus of the class. So that's a very good question because the whole focus of this class is we don't know the mash of implications to begin with. We're trying to figure out whether that whole mash of implications is whether it exists or not. In other words, this cloud here is what we are trying to find. Can we find a mesh of implications to connect between A, B, C and the proposed theorem of D? If such a mesh does not exist, then we also prove once and for all that D is not a theorem. If such a mesh does exist, then D is a theorem. Yes. No, 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 no. We are not going to go to those analogies because they really do not apply. Yep. Hmm? No, this is definitely not a black box. We will figure out one way or another whether there exists a mesh of implications or not. Yep, yep, yep. That is the case. All right. So, given this is the context, some of you may know some Boolean algebra already. So, every rule in Boolean algebra is actually an implication. Okay. In fact, it is a double-edged implication, or it is an if and only if. So, I'll show you an example that you probably know already. Okay. So, A is just a general Boolean variable, and B is also just a Boolean variable. So I'm going to help you guys practice the alternative form of the Boolean operators. So when I use this symbol here, it does not mean addition, it means a disjunction. Is that okay? All right. Because this is a lot easier to type and also to write. Yes. Mm-hmm. So that's a notation question. I'm going to focus on what I need to convey first, which is algebra rules are essentially implications, at least in Boolean algebra. So we'll focus on that first, and then we'll go back if we have a chance to get back to the notations. Okay, so this is basically saying, or in Boolean algebra is commutative. Okay, you can exchange the order and it does not change the meaning or the outcome of the operator. Okay, we go like, okay, but instead of using an equality here, I'm using if and only if. You cannot do that with general algebra because with general algebra, you're not dealing with truthfulness. In other words, the plus is actually returning a numerical value. And you cannot use if and only if between two numerical values. But in Boolean algebra, if A or B is returning a value that is Boolean, and B or A is returning a value that is also Boolean, then you can use if and only if in place of equivalent to or equal to, because if and only if is really the same thing as equal to, but it only applies in Boolean values. Is that okay? So in this case, there are two implications already because we have this in one direction and then we have the other direction back. Another one, which is definitive, is you can say A implies B is A implies B if and only if not A or B. Okay, that is also definitive. It just has to do with how we define implication as an operator. So that means if you just look at Boolean algebra, there are a whole bunch of implications already. There's another one. Okay, this is De Morgan's law. Okay, the negation of A or B. Okay, if and only if not A and not B. So I'm going to put extra parentheses just to emphasize what we are negating. Okay, that's one of the rules of Boolean algebra. This is one of the De Morgan's laws, okay, because there are two parts to the De Morgan's law. This is one part of it. I'm just giving you examples, okay? There's a whole long list of these things, okay? If you think algebra using numbers is a lot to remember, Boolean algebra has more. and they can be very confusing. I'll show you one that is one that is not confusing, and then followed by one that is like super confusing. Okay, so this one you know already. Okay, A and B or C, if and only if A and B or A and C. Okay, and someone who just walked into this classroom would look at the last one and go like, okay, that kind of makes sense, okay, because in normal algebra, that is true as well. Because A times B plus C as a sum is really the same thing as A times B plus as a product, plus A times B as a product, plus A times C as a product. Okay, that works in normal algebra. But in Boolean algebra, this also works. A or B and C, if and only if A or B, A or B and A or C. That does not work in algebra, normal algebra, but it does work in Boolean algebra. Okay, so there are lots of little things like these, and then there's a whole bunch of things that can help you simplify things. Okay, for instance, A or A, if and only if A, okay, and then you have A or not A, if and only if one, okay, because if you have a disjunction between any Boolean value A and the negation of that, that means one of them has to be true, okay? And if one of them has to be true and you're ORing those, then you always end up with a one, which is a true, okay? So there's a whole bunch, okay? I'm not going to list every single rule in Boolean algebra because I don't have to, okay? So the whole point is let's simplify things so that we don't have to do something like this. So the way we look at these things is from a quote unquote semantic perspective. So what do I mean by a semantic perspective? Let's pick one that looks really odd, okay? Let's single out this guy here, okay? I'm singling out this particular rule. And the way I say it, we use a semantic way to look at this has to do with I'm sure some of you are going like, okay, that just doesn't look right to me, okay? Because in normal algebra, it doesn't work out, okay? So you're gonna go like, tech, how do you prove that this if and only if is true? So what would be the answer to that question? A truth table, very good, okay? So this is what I want um, you guys to learn to do is when I give you something, when I claim something is true, okay, when I give you a statement and go like blah 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 is true, okay, try to use your own way to validate or verify that statement. Okay, in this case, a truth table is all we need. So let me draw a truth table here. So the truth table has three independent variable A, B, and C. How many rows do we have for this truth table? How many? Well, the last column, there are two more columns. So the one column is A or B and C, and then one column is A or B and A or C. Okay, so there are one, two, three, four, five. There are five columns. But what about the number of rows? How many rows do we have in this truth table? A, B, and C are independent variables, which means the truthfulness of one is not influenced by the truthfulness of the other two. So how many rows do we have? How many ways can we assign zeros and ones when there are three digits? Hmm? Eight. No, eight. It is 2 to the power of 3. Okay? Okay. So this is also, yeah, go ahead. The if and only if can only be shown when we look at these two columns and they all end up with the same value for every single row. So if that is the case, then we have shown that the if and only if is true. Okay, but we still have to work out the table first. Okay, so but I need to first address the question of why there are 8 rows here. Yes, go ahead. It is A plus B and A plus C. I ran out of space on my tablet. Okay, if that bothers people, I can redo that part. Okay, let me just get rid of the whole thing and redo the whole thing. Okay, so we have A, B, C, and then we have the left-hand side, which is A or B and C. I don't even bother with a dot now. And then on the other side, we have A or B, the whole thing, and A or C, the whole thing. So same number of columns, just a little bit more compact this time. Okay, there we go. All right, but I want to address why there are 8 rows in this case. Um, it depends. There are many ways to explain it. Okay, and from what I have heard from some people, they hate it when I say there are a lot of ways to show the same thing. Okay, because now it's like, but which way is the right way? They're all right. Which way you choose or which way works best for you is up to you. Okay, so I'm gonna switch to a different slide first because in this case, this is why CISP 430 and CISP 440 are kind of related because I'm gonna use a tree representation. Okay, what I'll do is I'm gonna go like, okay, A, B, C. Okay, so I'm gonna start with a root node here. So from the root node perspective, I can say, oh, A can be true or false. I think I might have given you a tree like this before, okay, but I'm gonna do it again. So for the second level of the tree from the root, it's about B, okay? So when A is false, B can be false or true. When A is true, B can also be false or true. So false, true, okay? Now I can say if A is false, B is false, C can still be false or true. When A is false, B is true, C can be false or true. When A is true, B is false, C can be false or true. And when A is true, B is also true, C can also be false or true. False, true, false, true, false, true, false, true. And that enumerates, okay? It basically gives you the all 8 ways of assigning true false value to the 3 variables A, B, C. Is that okay? Is that working? Okay. Because this is the visual representation of why the total number of rows that we need to work with is 2 to the power of 3. Because every level of the tree is multiplication by 2. Yep, that would be 2 to the power of n. That is correct. N being the number of variables. Yep, that is correct. All right, so now that we know why there are 8 rows, we can now go back and work on those 8 rows. So when A is false, 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 true, 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 B can be true, false, false, true, true, false, false, true, true. When A, B are in a particular configuration, C can be false, true, false, true, false, true, false, true. There we go. And if you are taking CISP 310 and you go like, oh, that looks like a binary number counting from 0 to 7, you would have been correct. So, but you can see how classes are related. Okay, things are not siloed. Okay, everything is related to quote unquote everything else, especially when you're talking about computer science as a subject matter. So being able to recognize it's like, oh, we are looking at 0 to 7 as binary numbers. That's great. Okay, because you're reinforcing not only what you're learning in this class, but also what you might have learned already in a different class. Okay, so now we evaluate everything here. Um, so if this is a 0, okay, because if you evaluate the whole thing, it's a 0. This is also a 0. This one is still a 0, and put a 0 here. This one is a 0, put a 0 here. This one is a 1, put a 1. This is also 1. Okay, do we understand why they're both 1s? Because if B and C are both true, B and C is true, but because B and C is on the right-hand side of the disjunction, so that means one side of the disjunction is true, the whole disjunction is going to be true. On this side, when you look at A or B, B is true, so A or B is true. When you look at A or C, because C is true, A or C is also true, then you end up with true and true, which is also true. So they are both true, but for different reasons, okay? So now we look into the next one, and that is also true because anything that has A in it is going to be true because for these 4 rows, they just have A by itself. But on the other side, because A is also common to both of the disjunctions, so that means both disjunctions, this one and this one, they're guaranteed to be true already because A is common between them and A is true. So that means we also know that these are also true. Question? Say that one more time. So we're looking, I think you talking about distribution, and there is this, well, this is distribution already, but the way it is A or the conjunction of B and C is the same in all 8 cases as the disjunction of A and B and the disjunction of A and B. Mm-hmm. Yes. I'm not sure what A and A where that comes from. A or B and C is on this side. But so you're trying to use Boolean algebra to prove the equivalency between these two statements. Yeah, that defeats the whole point of this entire discussion. I'm using truth table because because a truth table gives you the meaning of the operator and the expressions. That's the meaning of the whole thing. Yep. Aside from a truth table, you can use Boolean algebra to do that too. So in other words, if you use Boolean algebra, you can expand this using the other distribution and end up and doing some simplification, end up with this. But it's kind of like a circular kind of reasoning. But in Boolean algebra, the nice thing is, a lot of things can be proven using just a truth table. Okay. Yep. No, these are all Boolean. No, the plus is a or. What looks like multiplication is an and. Yep. I'm just trying to save myself a little bit of time. Yep. Go ahead and then go back. Yep. Okay. Sure. Okay. So the other simplification, the other distribution is this one here. So that means A or okay, A or B and A or C. If I do a FOIL on this one, it becomes A and A or A B and A or A and B or B and C. Okay, does that? Yep. Okay, that works. Um, oh, okay. So that's A or BA or AB or BC. And then because AB and BA are the same thing, so I can look at those and combine both of those into one. So now you guys think that I'm stuck, but there's another Boolean algebra rule that says A or AB is just A. So now I can simplify these two into just A and an or BC. Okay. So I know it looks really kind of circular, okay, because I'm using algebra to prove axioms of Boolean algebra. Yep. Because I'm trying to illustrate what it means to be semantic. Every time you look at the truth table, every time you look at the actual truthfulness of an expression, you're looking at the semantic. You're looking at the meaning of the expression. Okay, does that answer the question? No, it's still consistent with everything in the module. We are just skirting around what is already in the module. Yep. Well, I'm trying to explain the difference between semantic and syntactic. Because when we perform Boolean algebra, we are looking at things from the perspective of semantic. We're looking at, oh, if this is true, is that going to be true, and so on. And in order to show the equivalency between two expressions, we can utilize a truth table. From the perspective of the raw mechanism of propositional logic, it is completely syntactic. In other words, every time you see A or B, okay, it would say, oh, it is the same thing as B or A. It does not understand why that is the case. It just knows that syntactically, A or B, B or A can be, one can lead to the other. So that's the difference between the semantic perspective and the syntactic perspective. In Go ahead. I'll let you guys answer the question, and then we'll go back to the first one and ask. It looks simple to you. It seems to make sense because it is in normal algebra, but is it actually true? Okay, so we'll go back to that one after I answer a few questions. AB plus BC part. AB plus BC. Okay, so BA and AB are the same, so I only need to keep one of them. So I keep AB because of commutative. Because okay, so there are a few rules that I did not specify. Um, A or A is just A. Okay, that's also something I did not specify. And then we have, A, B equals to BA. I also did not specify. So there's a bunch of algebra rules that were used in the process that I did not blah blah I did not specify. Yep. Um, why isn't there an AC? Oh, there is an AC. Very good. That's fine. Plus AC, but AC is also absorbed into just A because of this rule here. Yeah. So yes, you are correct that I neglected to write AC, in the FOIL, but it is also true that AC can be absorbed into just A. Now you guys go like, that just doesn't look right, right? Okay, because outside of the context of this class, if I just say A plus AC is just A, most of you would go like, that's not true. I can find plenty of examples where this is not true. But what if everything is in the context of a Boolean expression? In other words, the plus is an or, the what looks like a multiplication is an and. Okay, you go like, it still doesn't look right. Well, it may not look right, but if the truth table works out, then it is still true. Yes, it is basically okay. If you think about, okay, how many people know what is regular expression? Okay, we got a few hands. All right. So I'm not going to teach regular expression in this class, but it is super important. Okay. So you need to, find a chance and opportunity to learn that. Okay. You can use ChatGPT to help you learn that. Okay. But nonetheless, you still need to learn that. Okay. So getting back to the discussion, okay, which is the way we look at things is from the perspective of semantic. When we look at an expression, we want to know whether it is true or not. When we look at two expressions that are equivalent, we want to use a truth table to show that for every possible way, they turn out to be the same. And even the first one, okay, if you look at this first one here, you would say, it is intuitive. I know that already. Well, do you? Okay, because the equivalency between A or B and B or A is not quote unquote natural because A, B, A or B, B or A, this can still be done using a truth table. If you don't do it using a truth table, then you may not be entirely correct. So in this case, we have this as a truth table. So you now ask, oh, so now it makes sense, right? Because whether whether you express the disjunction as A or B, or whether you express it as B or A, you still get the same values for the operator. So even something as simple as that, the commutative law of disjunction is not just implied. Yes, go ahead. That is a very good question. Okay, so the question is, in order to turn what we see as an algebraic rule into just a syntactic thing, which means, oh, syntactically, okay, I'm gonna start a new page two. In order to say, oh, if I say see something, a pattern like this, I will automatically infer that this is this. The question is, what if I do something like this, but it is not consistent with the actual meaning of the operators? Then you end up with a propositional calculus system that is useless. Because in that case, the syntactic quote unquote transformation, this symbol means infer or it transforms to, which is a syntactic operation. It simply says, oh, we have a or here. Whatever is to the left-hand side of the or can switch to whatever is on the right-hand side. And according to the syntactical rule, they should still be the same. But it has no actual meaning behind the whole thing. It is just a syntactic operation. Yes. No, the other way around. Because the computer has no understanding of what is an and or what is an or. It just knows how to match patterns. So the whole point of propositional logic system as a system is we are converting something that requires understanding, intuition, and understanding the meaning of things into something that is strictly mechanical and syntactical. Yep. Well, it's actually the opposite. We're not going to use truth table. We are just going to use symbolic manipulation without understanding the truthfulness behind everything. Everything boils down to just symbolic processing. But that's because what are computers really good for? Symbolic processing. String copy, string cat, okay, um, string compare, right? Diff, okay? Those are all symbolic operations. Are we doing okay so far? Okay. So if you look into the derivations, We can do a whole lot of things that are somewhat stupid, okay? But this is I need to talk about something else at this point to resynchronize with what is in the module. So when you look at a propositional system, usually it is expressed as a lambda, okay? It's a four tuple. It has alpha, it has, okay, I'm trying to remember all the symbols here. It has, I cannot remember, is it omega first or iota first? Omega first, okay, omega, iota, and zeta. I think zeta is the last. I got it already on? Okay, okay, so let's backspace. Okay, zeta and iota. Okay, it kind of makes sense that way too. So it's a four tuple. Each one is a set. Okay, so each one is a set, and together they define a specific propositional calculus system. So you can think of the propositional logic system as a function. Okay, it's just a function. It has four parameters. These are the four parameters. And when you call that, it will basically give you, and you need one last one, which is a statement that you need to know whether it's a theorem of this entire system or not. So it's a five parameter thing, and it will return either true or false. True if and only if the fifth parameter is in fact a theorem, and false if it is not. Okay, so think of that as the objective. So we'll explain each one of these. Okay, alpha as a parameter specifies symbols. Okay, so this is all about the symbols. So typically, okay, we usually have false or true, using 0 and 1, as symbols. Now, if you say I really prefer to use the word true and the word false, fine. Okay, do it your way. But I prefer to use 0, 1 just because it's easier to write. Okay, and type. Okay. And typically we use English alphabet like P, Q, R, S, T. Okay, you can use a number of these, but these are called variables. And we talked about variables at the very beginning of the class. So each one of these variable is a Boolean variable. Now, is the variable true or not? We do not know, and nor do we care. We just know that each one can be true or false, as opposed to the constants. 0 can only be representing false, 1 can only be representing true. Okay, and then we have some Greek letters here. This is theta. We can have psi. I like psi a lot. And also we can have rho and a bunch of other ones if you prefer. Okay, but we'll just kind of simplify the whole thing and have the three Greek letters here. Alpha, not alpha. We have theta, psi, and rho. Okay. Usually I use phi too, but it doesn't really matter what we put here. So we have these as constants, these as variables, but these three are called schematas. Schemata. Okay, they are strictly used for pattern matching purposes. In other words, we don't get to use the Greek letters until we get to specify what is in zeta. Because zeta, okay, what or z, okay, you can call these things using its English name, I don't care. So zeta is about transformation rules, and the transformation rules are all about matching patterns. Okay, so we won't get to use the Greek letters until we get to z. Okay, it will be utilized in z. All right, so that's that. And now we go to omega. Omega are called, each element of omega is a connective. Okay, that's one word to call that. But in programming or computer science, we simply call those operators. So every element of omega is an operator. So now what operator you want to include? Well, it kind of depends on how complicated you want that system to be. So So we typically include negation, conjunction, disjunction. But if you want, you can also put implication, equivalence, blah, blah, blah into it. But those are the operators. Are we good so far? Okay, they're just operators. So now between alpha and omega, I can now define what we call well-formed formulae. Okay, but before we go there, we have to kind of look at a subset called alpha. Oh, there's no zero here. There's omega 1. So omega 1 is a subset of omega where it only consists of operators that require one single operand. Okay, in this case, the negation is the only one that requires one operand. Everything else requires two operands. So omega 2 would be all the operators that require two operands. So we have and, or, implication, and if and only if. Okay. Now, why do we have to break omega into omega 1 and omega 2? The reason has to do with if I want to use a formal language to describe what is a well-formed formulae, then these become useful. Is that okay so far? All right. All right. So with these you're already defined, with only alpha and omega defined, I now define what is a well-formed formulae or well-formed formula. Okay, WFF, not WTF or WWF. It is WFF, well-formed formula. Yep, quantifiers. No, we do not do quantifiers in propositional logic. Go ahead. Um, it does not exist in propositional logic. Yep, it just does not exist. Okay. So WFF stands for well-formed formula, and this name was coined outside of the context of computer science. So from our perspective, you can say a WFF or a well-formed formula is simply a syntactically correct expression. Yes. It so the reason why we have to break it up into omega 1 and omega 2 is because we need that to define well-formed formula. Because we have to make sure that we are providing the correct number of operands to an operator in order to is a test. See, I'm not affected at all. And of course, the district will look at this as a problem. It's like, if anything is happening, geotac, you won't know about it. Yeah, but my students will tell me. And my watch will tell me because it's calling me about a test. So we can just turn it off. Okay. Um, right. So from our perspective, you can say, oh, WFF is really just saying that an expression is syntactically correct. Okay. So what is not syntactically correct? Okay, let's look at something that is not syntactically correct. That is not syntactically correct because conjunction needs two operands. Okay, I'm only giving it one. That would also be not syntactically correct because negation is only using one operand and I'm giving it two. Yes. Can it be read as what? Not so when I use this, I'm using the strict propositional logic, operator way, and not using the simplified way. Yes, but I'm not using that in this context because right now, the syntax becomes important. So I have to stick with the stricter. Yeah, you can use parentheses. Yep. Okay, so now we want to look at what are well-formed. So P is well-formed. Okay, this is well-formed. P or Q is well-formed. P or P, the whole thing, or P is also well-formed. Because when you look at the or, oh, I just said that I'm supposed to use the stricter um, Boolean operator. So I do apologize for conflicting with what I just said. Okay, fine, we'll just use the actual operator. Okay, but this is syntactically correct. Yes, go ahead. I use that a lot when we do not have to deal with the syntax aspect of an expression anymore, because it's just a whole lot easier to type and write. Especially when you need to turn in homework assignments, where you have to type in a lot of Boolean expression, it saves you a lot of trouble of not having to deal with these symbols. Yep, yep. So the last one here, P or P, is actually syntactically correct because when you look at the or, do we provide exactly two operands for the or to operate on? Yes. This one, yes. The middle one, also has two operands, and then the one to the right-hand side also has two operands. So it is syntactically correct. The question is it useful? No, they're really the same thing as just P, okay? But remember, in propositional logic, we do not look at the meaning of things. We do not look at the semantic of things. We only focus on the syntactical aspect of things, okay? So are we good so far? Yes. Yes. We are setting up the grammatical rule for what is a grammatically correct Boolean expression. Is that okay? Yep. So you can make a propositional system that is not just based on these operators. I cannot imagine what else you want to add to it. So instead of adding things to the proposed propositional logic system, we will end up simplifying it. Okay, so that we are going to avoid a problem that we're going to get into in just a few minutes. Okay. All right. So now we want to kind of look into this, the concept of a space of all well-formed formulae. Okay. So I'm going to use this as a space of, okay, a space spanned by alpha and omega. So this term, spanning is coming from linear algebra, because you can span a two-dimensional space by using two vectors and stuff like that. So it's being used in that sense. Okay, you have two things, and when you combine those two things, you get um, you generate a space that is bigger, or at a higher dimension compared to the two things that you are trying to the two spanning vectors, or the how do you call those things? The orthogonal vectors. Okay, but in this class, it's not kind of like that. Okay, so let's just say that S is the set of all the space already spanned by alpha and omega. So that means S is basically the set of all WFFs. It's basically a set of all the well-formed formulae. Um, so what do you think of the size of this set here? I just need to know, is it finite? Now, if you just look at the way we define alpha and omega, okay? So the way we define those two is omega is just a 5-element set, and alpha is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's a 10-element set. So when you look at each individual one, alpha is finite, okay, 10 elements. Omega is finite, it only has 5 elements. But when we look at the set of all possible well-formed formulae, what about that one? Is it a finite set or is it an infinite set? Yes, it is an infinite set, okay? I don't even need that many symbols to generate an infinite set. I just need or and one single variable, okay? Because I just illustrated that in the previous example, okay? So I can reapply this and say P or P or P or P. So this is where, being able to copy and paste is really helpful, okay? Because I can now say copy this and paste here, okay? And then we put an or between those two. So do you think the new expression is also well-formed? Yes. And I can keep doing this until the end of time or doomsday, right? So that means the space is infinitely large. So can anyone relate this thing, okay, the thing that I'm just talking about, to what we ended up talking about in the previous class, at the very end of the previous class? What did I talk about in the previous class? Something about horses and no, I did not talk about horses, but I did talk about something that well, I want to see how your brains work, okay? No, haystack, horses, haystack. Uh-huh. Okay, what about haystack? Is the haystack infinite? You're supposed to find a needle, okay, or a needle that is labeled in a certain way in a haystack. Now, if the haystack is finite, it's not a problem. It may be just time consuming, but eventually you will say, yep, I searched through the whole haystack, the needle, it was not here, okay? But if the haystack is infinitely large and you're supposed to find a specific needle, then you can never come to a conclusion. Yes. Nope. Nope. Has nothing to do with short circuiting. Yep. Hmm. Well, but we are not going to put restriction. Well, okay, so yes and no. Okay. The way we put a restriction is, I can only talk about the restriction after we talk about CNF or conjunctive normal form. But until we talk about conjunctive normal form, there's no easy way to express, what the restriction is in the form of. Yep, go ahead. Um, well, first of all, I redefine what is well formed. Okay. And once I redefine what is well formed, then I can say, oh, we are only restricted to use these things. Okay, only these things are supposed to be well formed. But then the question is, with that restriction, can we still express all the um, common Boolean expressions that we have to deal with? So that becomes the question, right? So we'll answer all of those questions when we get to that point. So the problem is, in this case, the cardinality of the set of all the well-formed formulae is actually infinite. Now, I know mathematicians will frown at this because nothing can actually equal to infinity, but I'm just going to use this to represent that the number of elements in S is infinite. Are we good so far? Which is the problem. Okay. So propositional logic is a great thing to formalize how we approach logic because everything is very rigid. It is syntactical and everything is very rigid. But from the perspective of computation, okay, when we want computers to prove theorems, it becomes a problem. Okay. Yep. Mm-hmm. You can have simplification transformations, yes. But the problem is which transformation are you going to apply? Yes, you can specify those rules, but the question is which rule are you going to apply first? Okay, so let me go kind of skip a bunch of stuff and then go to Boolean algebra. Algebra, okay. And there are a few of these. Okay, there we go. Okay, I like this one. I like it when somebody else has already written this, so I don't have to write it myself. So I can focus on things that I really want to write about. Okay, blah, 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 blah. Blah, 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 blah. There we go. So we have, keep going. You can see how this is really kind of complicated. And what I want to do is to get to the actual number of transformations. There we go. Okay. All right. So this is a table of transformations. In other words, if you can find a pattern to the left-hand side of this funny looking T symbol, it is called infer. Okay, when you see this symbol, it means the left-hand side infers the right-hand side, which is not the same as implication. Because when we use the word infer, it means we are only concerned about the syntactic aspect of the expressions. Yes. No. The problem is not the rules. The problem has to do with which rule do you fire when multiple rules can be fired at any particular time. Okay. So what we are doing is we are looking at things that are already true or statements that are already true. And then we are looking at these rules, transformations, and then we ask which one can fire. There are all usually multiple ones that can fire. Now the question is, which one should we go first? It's the prioritization of which rule do we want to fire first. Yep. No, these are elements of zeta. Yeah, these are elements of zeta. But what I want to do is to talk about, from the human perspective, these rules are all human based. Okay, these are all reflecting the way we perform reasoning. Okay, so the first one, it doesn't use the same symbol that we use because I use single arrow for something else. This is saying P implies Q and P infers Q is true. Okay, now it is syntactic. Okay, it means if you can find an implication that is true, and it turns out the implication is true, and whatever is on the left-hand side of the implication is also true, then you can conclude whatever is to the right-hand side of the implication is also true. But it is looking at things from a syntactic perspective. It doesn't care about the actual meaning of implication. So what do I mean by the meaning of implication? The truth table. So these are all syntactic operations. And you can see that there's a long list of these things. Okay. So who wants to remember these rules? Not me. And in order to make use of these rules, you also have to know which one you can fire. And if there are multiple ones that match and can fire, now the hardest question is which one should I use? Because you're not just matching these patterns and firing these rules randomly. You're trying to get to a specific statement that you want to find out whether it is a theorem or not. Okay, so let's take a step back. Okay, let's take a step back out of the context of this class. You have all taken math classes where you were asked to prove theorems. Is that true? Okay, because someone who says, no, I have never encountered a math class that I was not asked how to prove a theorem, I'm going to say, I don't think you meet the prerequisite requirement of this class. Okay, so what is the biggest challenge when you need to prove a theorem? It can be your calculus class, can be your linear algebra class, can be your differential equation class. It doesn't matter which class we are talking about. What is the most challenging part of proving a theorem? Yes. Well, that's the nature of a proof. That's the nature of a mathematical proof is, it's a rigorous process where once you prove something, you're not proving only a specific case of instantiating the variables, you're proving the case of it doesn't matter what the variables have. If this is the condition we start with, that condition is a result of the first condition. Okay. So that's kind of, it's by nature, it is part of what a proof is about. But what is the main challenge of theorem proving? Yep. Having enough paper. And why do you need that much paper? Because, yes, they're exactly. So at any point, so let's just think about algebra. Okay. So this is not an algebra class, but let's think about algebra. So if I want you to prove this expression in normal algebra can derive to this one over here. Okay. I'm sure most of you have proven algebra problems before, right? So what is the challenge of that? It is at any time, given any expression, there are multiple ways to proceed. So should I use distribution or should I use commutative law or should I use associative and put the parentheses pair somewhere else? You have all of those choices, right? So that becomes the problem. What if, I know we are running out of time and you guys are about to start, some of you are ready to start your spring break, but let me just put this one in. And I think I'm wasted not being a politician because I can make a very good politician. What if I change the system so that there's only one rule? Not only that, the space that is spanned by well-formed formulae is finite. Would you elect me in that case? So that's the whole thing, okay? So we are taking a system that was designed for people, for humans, okay, to basically formalize the process of logical thinking. I'm taking that and converting that into a system where there's only one rule that you need to consider whether to apply that or not. And the total number of well-formed formulae is also finite. So if I need you to prove a theorem, you only have to go through a finite number of steps to come to a conclusion, whether that statement is a theorem or not. Yes. So everything still has to be syntactically correct. Okay. But after I make a modification, the restriction of what is syntactically correct is a little bit more restrictive. And that really helped to um, limit the space of the well-formed formulae. It also boils all the transformations down to one single rule. So you don't have to say, should I apply this rule or this rule? Nope, there's only one rule. Yep. So we'll get to that after the break, in which case everybody is going to forget what I just said today entirely, except for the horse. It's like, what about the horse? We didn't talk about horses. Yes, we did not. No, we did not talk about horses, but we did talk about haystack. That's close enough. That's relating. Yes. Yeah, I know. But BNF is a special case of general transformation because, okay. So with BNF, okay, so okay, so when you look at BNF, you have a token T1 and it expands to T2, and then you can give it a terminal of whatever ABC, and then another token say T3, right? So that's generally speaking what a BFF rule looks like. That's transformation. Think of it this way. This is really the same thing as saying T2, ABC, T3, and inverse, T1. It's still pattern matching, except when you look at BNF, the pattern matching always ends up with a specific token, just one single token, as opposed to general propositional logic, where you can have both of these components reappearing here in just a different organization, and you can even have these things repeating themselves when you on this side. Not exactly. So what would consider to be a schemata would be the use of this, that those are schemata. Because you're referring to a matched pattern. You are designating a specific matched pattern. So on one side of the infer, so on this side of the infer, okay, you use these. On this side, you use these. Mhm. Yes, so you basically just turn it into prefix format. Yep, yep, yep. But we are turning everything around so that we do not have to deal with this. What is arity? Oh, arity. Okay. So yes, so the arity of an operator determines which omega group it belongs to. Yep, yep. Okay. Yeah, I will go back to my office, but I have to kind of stay here a little bit. I have to shut down stuff first. Yep. hmm Since I'm here, I can answer questions. Yep. Okay. You can follow me to the office. Yep. Or you can send me an email if you want to do it that way too. Okay. Okay. So you're gonna have to follow him because he started the question first. Um, yeah, go ahead. No, it is to automate what we need to do using um, syntactic mechanisms. Because when you try to prove a theorem, you're using the semantics in your head. It's like, oh, this expression is the same as that expression, and so on. But the computer does not care about the meaning. It only needs to know, syntactically, can this transform to that? So that's a syntactic perspective as opposed to